non-periodic part, but that's a finite. That's the finite part. Then you have a block of length k, which repeats infinitely often, so which repeats infinitely. So that's the periodic continued fraction. And when we expanded square root of 7, I think in the first lecture, we saw that it's a periodic continued fraction. We expanded square root of 2, that was also periodic continued fraction. We expanded golden ratio, which is 1 plus square root of 5 by 2. That's also a periodic continued fraction. We have seen this. So that's a general fact. That's a general fact that all these, what is called a quadratic shard, so that's a real solution of a quadratic equation with integer coefficients. So those are called shards. So they are of the form a plus b square root of c by some d. So that's the form. And they are all periodic continued fractions. So let's start by proving one side of it. In fact, I won't prove the other side. Just skip the proof. So let's see the. So a periodic continued fraction periodic continued fraction is a quadratic shard. It's a quadratic shard. So that means it's a real root of a quadratic equation with integer coefficients. So let's see that. So proof. So let x be a periodic continued fraction. We use the notation we already wrote above. So AL minus 1. So that's the non-periodic finite part. And then we have the repeating part. Sorry. So that's a length, k length block. So it's starting from AL. So it should go up to AL plus k minus 1, and that this the bar notation denotes that this block of length k repeats. Now this is our standard notation actually, so I don't really like it. So AL dash is, or maybe so this is what we were writing. So A1, A2. So whenever you cut at L length, then what you have to write here is the complete quotient. So AL dash. So that was our notation for the complete quotient. So complete quotient the Lth complete quotient in this case stands for the periodic part. So AL dash is, so if you write it out, then it starts from AL, you have AL plus k minus 1, then it starts with AL again, and just the same thing repeats. So you can as well write this. So think of this part as a continued fraction, the right hand side of the last line. So then this is AL plus k minus 1 AL dash. So this is the same AL dash. So that same complete quotient is sitting there as well. So you can write that because of this infinite repetition. Now recall this fact. Recall that x is equal to an plus 1 dash pn plus pn minus 1. So all with our previous notations. A dash always represents the complete quotients, and Pn by Qn are the convergence. So Pn is the numerator of the convergence, Pn minus Qn is the denominator of the nth convergence. So we use this for also, we know this for all n. So just recall that. So we use it here. So just think of this as this one, the last line. This is where we use it. Just think of this continued fraction. So it's a finite continued fraction now because AL dash replaces it. It stops here. So AL dash is the repeating part. So just think about the last line and use this this thing, what we just recalled. So if you do that, then AL dash. So using this fact, so AL dash is equal to. So this formula has just the previous. So if you have this n plus 1th complete quotient, then you have nth and here n minus 1. So just the previous two. But for this one, we don't use any notation back because that will not match with the notation of the original continued fraction. So we write it in this way, that AL dash, that's the that's this last complete quotient, and then what we write is. So this has to be multiplied by, let's call it P dash and then P double dash. We don't need to give it a name actually. AL dash Q dash plus Q double dash. So what are these? Just following this, let me just write that. So where? Okay, maybe with the same color. P dash, sorry, P dash, not P1. P dash by Q dash and P double dash by Q double dash are the last two convergence. Last two convergence of this fraction AL plus K minus 1, this continued fraction, just this finite continued fraction. So these are the last two convergence. So A dash by Q dash is the last one, and A double dash by Q double dash is the previous one. So they are last two convergence. So we use this notation, and they are integers because all these are integers. L dash is not an integer because it's a complete quotient. Complete quotients are not integer, not necessarily integer. Most of the time they are not, but all others are integers. So these are integers. So we have this. Now what we have here is an equation in AL dash. So let's start from here. Let's just give it a name. So from 1, so what we get is, so I just change side. So AL dash squared Q dash plus AL dash Q double dash is equal to AL dash P dash. Oh, 1 second. I have one second. Sorry. Yeah. So what? Okay, this doesn't look like 2. So we have AL dash square. So I'm multiplying by AL dash. So we have AL dash square Q dash Q AL dash Q double dash, and on the other side we just have this Q dash. So we have AL dash. Let's write it like this, because we have this dash and also the square. Q dash plus AL dash. Okay, so AL dash has coefficient Q double dash minus P dash. Sorry, this is P. Okay, sorry, this is minus P dash. Minus P double dash is equal to 0. So we have AL dash satisfying this equation with integer coefficients. But what we have to now see is that how AL dash is related to AL. Sorry, the original continued fraction, which is X. So let's rewrite that, and that will prove the theorem. So once. So let me call this equation 2, and let's try to connect X to AL dash. Now we know that this is the notation we are using, that A naught, A1, etc. That AL minus 1. Then we have this part which is the complete quotient at AL dash. So this is what we have. Therefore, this is AL dash with the same notation that we recorded. So just this is using exactly the same thing. So that's the lth entry. So AL dash, then we should have PL minus 1 plus PL minus 2 divided by AL dash QL minus 1 plus QL minus 2. So that's the relation between that's the relation between AL dash and X. And therefore, we can express AL dash in terms of X. So just write it down. So we can, if you just solve this linear equation, then what you get is PL minus 2 minus QL minus 2 X, if I have done it correctly, possibly. And then you have QL minus 1X minus PL minus 1. PL minus 1, yes. So let's call this 3. Now, AL dash is expressed as a quotient of two linear forms in X. And AL dash satisfies this quadratic equation. And all the coefficients involved are integers. Therefore, we can just combine this equation 2 and 3 to say that X satisfies a quadratic equation. So combining 2 and P, we get a quadratic equation in X. So we get a quadratic equation in X, quadratic equation in X with integer coefficients. That is important. So X is a short. So that proves the theorem. So that proves the theorem. So what should be the converse? So converse, so converse. So what should be the converse? So this what we proved is if we start with a periodic continued fraction, and then we started with a periodic continued fraction and proved that it satisfies a quadratic equation with integer coefficients. So it is a quadratic sort. And the other direction is that if you have a quadratic sort, then its continued fraction expansion is periodic. So continued fraction, let me write the statement. We know the uniqueness, so let's call it the continued fraction expansion continued fraction representing quadratic sort is periodic. Okay. So I'm going to skip this proof. So that's also a theorem. So this proof I'm going to skip at the moment. So proof, for proof you can just see Hardy, right? So that's essentially that's the textbook I'm following. Hardy, right? So yeah, please see Hardy, right? So I don't want to do actually with too much of theory, so I would skip that. Rather, I would prefer to talk about an example. So let me let's start talking about an example, though I need a little more theory to really do justice to it. But let me just start with the example. That's a very nice, motivating example. Yeah. So example again. Just draw a line and so we have an example again, or you can say application. Yeah. So that's again an interesting problem. So to pose the problem, we need to know what is a triangular number. So I guess most of you already know it. Let me just quickly say what it is. So triangular numbers are numbers formed by this kind of a diagram. So you can start with one dot, and then we are just trying to form a triangle. So just add this and then this. So you are placing dot at you are extending the edge and putting dot in between. That's the structure. So it's just like stacking oranges. So this, and so at each step you increase it by 1. Yeah. So this. So at each step you are increasing by 1. So then what are the triangular numbers? So triangular numbers are numbers like this. So you can just have this triangle. So first triangular number is going to be say 1. So that's the first one. That's not a triangle, of course, just the beginning of the process. And then the number is 3. So apart from the first one, everything else has to be really a triangle. So then we are adding 3 to it. So that's a 6. Meaning we have extended it to this. So every stage gives us a triangular number. And then extend to the next stage. So you always get a triangle. So extend it to this. So that's 4 more. That is 10. And then you have 5 more. So 15. And it goes on like that. So the next one is going to be 21, etc. Now the question is, when do we have squares in this sequence? So this obviously gives an infinite sequence of integers. The question is, when do we get square in this sequence? When does a square appear? What are the squares appear? Do they appear at all? Because a priori there is no reason that there would be squares. When does a square appear? Or if they appear, then how many are there? So you can ask all these questions. So I'm just writing one so we want to look for squares in triangular numbers. So triangular numbers gives you an infinite sequence of integers, and we are looking for squares in that. How do we go about it? So by definition, what is a triangular number? So the kth triangular number is going to be 1 plus 2 plus 3 plus etc. to k. So that's the kth triangular number. And we know how to sum this. So this is k into k plus 1 by 2. That's the sum. So all the triangular numbers are going to look like this, k into k plus 1 by 2. And of course, 2 divides either k or k plus 1. So it's always an integer, obviously. Now the question is, when is it a square? So the question now turns to be this, that find m, or say that the question implies that so question asks us to find an m such that k into k plus 1 for some k is going to be m. So in other words, we need to solve this equation for k and m. Same thing as saying this. So solve this equation, k into k plus 1 by 2 equal to m for k and m. Yeah. So now how do we go about solving it? So to solve it, of course, we simplify it slightly. So we work with the equation.
It's m square or m?
Oh yeah, of course, of course, of course, of course. Thank you, thank you. That doesn't make sense. Yes, this is m square. That's what we are looking for. It has to be a square. Yes. Yeah. So therefore, let's write down the equation again. 2 is equal to m square. That immediately gives us k square plus k is equal to 2m square. So you want to complete square on the right hand side. So let's multiply this by 4. So 4k square by 4k equal to this is so 2 times 4m square. Just writing like this because 4m square is a perfect square. So this I can write as 2k plus 1 whole square. Now that gives an extra 1, so I must subtract 1, and we have 2, and then 2m whole square. That's the reason I kept 4 here. So in other words, what we need to solve, so the question boils down to this problem. Let's solve this equation. X squared minus 2y squared equal to 1. So if I just interchange this, just change the sign. So it's enough to solve this equation. So let's try to do that. So some solutions can be observed. Okay, it can be easily computed with a calculator. So some solutions. For example, x equal to 3, y equal to 2 is a solution that we can immediately see. Some solutions. So x comma y is equal to 3 comma 2. 3 comma 2. 9 minus 8 is 1. So that's what it is. And then the next solution, I have a list, so I'll write it down. So 17, 12. That's slightly non-trivial, of course. And somewhat more non-trivial, 99, 70. And then the next solution is 577, 408. But if you use a computer to check this, it's not really too difficult. So these are the solutions. These are the first few solutions. There could be many, could be many, could be infinitely many. We don't know. We don't know now. We would know, of course, by the end of this discussion.
So real solution also exists, right?
Sorry?
A real solution. You write only the integer solution.
Yeah, I'm writing only the integer solutions. Yes, integer solution, only integer solutions. Yes, because we want this k and m to be integers, so we are looking only for integer solutions. Yes, so I should actually mention that. So because our ultimate goal is to find this integer k and m, so therefore we should look for integer solutions. Yes, so solve this in integers. In fact, solving equation in integer is what makes number theory difficult. So integer solution is very important. Okay. Now we know one of these numbers. We know one of these numbers very clearly. So just recall this. That so do you remember this number? So this one was, so if you multiply numerator and denominator by 3, then it is 297 by 210. So these are actually the proportions of the A4 size paper. So this is the length in millimeter and the width in millimeter. The denominator is the width in millimeter. And where did they come from? They come from convergence of square root of 2. So let's try to see if convergence of square root of 2 solve this equation or not. Let me make a table. So 2 is involved in the equation, that we can see. It's x square minus 2y square equal to 1. So convergence, so a priori unrelated information, of course, so we would relate it. Convergence. So if you look at convergence of square root of 2, then what we will get is the first one is just 1 by 1. Then you have 3 by 2. Then 7 by 5. You can use that online calculator to see this, check this. So 41 by 29, 99 by 17, that's what we just talked about. 239 by 169. 577 by 1. Yeah, I might have written something wrong here. So 408 1393 1393 by 985 and so on. Now observe that not everyone is a solution to the equation, but alternating ones are. This is a solution, this is a solution, this is a solution, and this is a solution. So alternating ones are solution. So this is just an observation. We haven't proved anything yet. So next thing is to try to establish this connection rigorously. So we do that. Okay. So for that we start looking at the continued fraction expansion of square root of 2. So how do we really establish this connection? That convergence provides solutions, and every alternate convergence provides solution. We also need to prove that we also need to show that this goes on. Actually, it gives probably it gives all the solutions, etc. So square root of 2 looks like this. So this we have already done. So we can write it as 2 plus, so I'm not just repeating the process. So this is like this. So 1 plus square root of 2. And then it goes on. So this gives a recursive way of writing the continued fraction, and just recall that, which follows from here immediately, that the continued fraction expansion is just this. So it's a periodic continued fraction, and with repeating 2. So 1 followed by repeating 2. That's the continued fraction expansion of square root of 2. So if you look at this, then it is 1, 2, And then you have a complete quotient, which is 1 plus square root of 2. So that is what it is. In fact, if you just iterate this same process, then you will see that. So this is in our notation, this is A1 is A0, A1, and then A2 dash. So this complete quotient. Now we can simply repeat this process, and you would see that if you just write AN, and then you would have this AN dash. So that's the way we write any continued fraction. And this is going to be, or maybe just put it in the bracket. So that's the notation. What we would get here is 1, 2. So it's a chain of n 2's. And then what you have is 1 plus square root of 2. So the same pattern goes. In other words, all complete quotients are equal to 1 plus square root of 2. So that's for all n. So all complete quotients are 1 plus square root of 2. Yeah, for n greater than equal to 1, not 0th complete quotient is the number itself, which is square root of 2. All others are 1 plus square root of 2. So now we want to use the formula we have already seen earlier. So let me just recall that again. So we have this x an plus 1 pn. So general formula. Pn minus 1, and the denominator is an plus 1 qn minus 1. Yeah, so let's use it in, oh sorry, this is complete quotient, an plus 1 dash. This is a complete quotient. That's the form. So x is square root of 2 here, and all the complete quotients are 1 plus square root of 2. Let n be greater than 1, greater than equal to 1, at least 1. Pn plus Pn minus 1, 1 plus square root of 2, Qn plus Qn minus 1. So this is the specific equation that we get. So let's just multiply it out. So multiplying this by square root of 2. So this is square root of 2 Qn. Okay, let me just gather terms as well. So this is the second thing is the integral one. So this is 2Qn plus square root of 2 with Qn plus Qn minus 1. So these two are getting multiplied by square root of 2. And you have, when you multiply the square root of 2 here, so that is a 2Qn. And the other side, the rational part is Pn minus 1 plus 1. And then you have the irrational part, square root of 2 Pn. So we equate the rational and irrational part. That gives us 2Qn is equal to Pn minus 1 plus 1 and another equation from the irrational part, Qn plus Qn minus 1 is equal to Pn. So we have these two equations. Oh, I think I wrote something wrong. Oh, yeah. No, this is not 1. This is Pn. This Pn is multiplied with. So this is Pn. It's not 1. Yeah, it is Pn. It is Pn. Pn. So we have these two equations. So these two equations. So let's write them side by side. So 2Qn is equal to, let's write it as Pn minus 1 plus Pn. And then we have on this side Qn minus 1 plus Qn is equal to Pn. Let's write like this. So Pn below Pn. Now what we want to do, we want to eliminate Pn minus 1 and Qn minus 1. Okay, let's start with this. So let me just give it a name. So that as such, it's an equation, two equations with 4 variables, but they are related. So that's what is important for us. I just call it 5. I think we have used up to 4, so let's call this 5 and 6. So multiply 5. Okay, let me write it like this, that we multiply 5 by Qn and then subtract subtract 6 multiplied by Pn. Yeah, so this is what I'm doing. So I'm just multiplying this by Qn, multiplying this by Pn, and then subtracting. So 2Qn square equal to Pn minus 1 Qn plus Pn Qn, and then multiply by Pn. So it is Qn minus 1 Pn. Okay. So Pn minus 1 Qn plus Pn square. Yeah, and this side is just Pn square. Yeah, so actually what we need to do that Pn square minus, so we actually change side. So you have Pn square written in this way, and you have 2Qn square. This is equal to Pn minus 1 Qn plus Pn Qn minus Pn minus 1 Qn minus Pn Qn. So Pn Qn goes away. You have Pn minus 1 Qn minus Pn. Writing something wrong.
Yeah, you did make a mistake in that. You multiply Pn, that is Qn minus 1. In the second equation.
Second.
Multiply by
equation.
Pn. And the sixth
Multiplying by
equation.
Pn. Yeah. So multiplying by Pn. So it is. Yeah. Exactly. So this is. Yeah. Exactly. Thank you. Thank you. So this is Pn. Yeah. Exactly. So otherwise everything cancels. Yeah. Thank you. So Pn Qn minus 1. It's correct. Yeah. So Pn, so there is a mistake here. Pn, this is Pn Qn minus 1. Pn Qn minus 1, Pn Qn, and then Pn minus 1 Qn minus Pn Qn. Yeah, it's correct. Therefore, what I have is Pn Qn minus 1 minus Pn minus 1 Qn. Now we know that this is this is nothing but minus 1 to the n minus 1. We have proved this argument. And therefore, so let me just write that again. So 2 Qn square is equal to minus 1 to the n minus 1. So these difference, so Pn square minus Qn square minus 2 Qn square is going to change sign. In fact, when n is odd, you get a plus 1. And when n is even, you get a minus 1. And therefore, P say 2m square, sorry, 2m plus 1, I just said that. So all the odd ones. This is going to be 1 for all n greater than equal to. Yeah, in fact, from first solution onward, it is just 1. So we can see. So this is the phenomena we observed, that the alternate ones are giving solutions to this equation. So therefore, P2m plus 1, Q2m plus 1. So this is a solution. So is solution to x square minus x square minus 2y square equal to 1. So these are solutions now. So we have infinitely many solutions. We have infinitely many solutions. We can also show that these are the only solutions. So I would probably not prove it in complete detail, but we can. But you can. Okay, I'll send you a reference. Actually, there is a book on all these quadratic equations, which is very nice. It just gives. In fact, a general Pell equation can also be. Okay. So let me just talk a few words about what the kind of equation this is. So these are called Pell equations. I looked up a bit of history as well. So that's a complete aside from the what we are doing. Just, so this is just a remark. So these are usually known as Pell's equation. Pell's equation. So these are of this form: x square minus dy square equal to 1. and of course it needs to be solved in integers. So D is generally greater than or equal to 1. In fact, strictly greater than 1. So solve solutions in integers. Let me just write solutions in integers. So what we are looking for is solutions in integers.
And D should be non-square integer.
Yeah, exactly. Yeah, because if it is a square, then you are essentially down to this x square minus y square. So solutions in integers. Yeah, so let me add that point as well. So non-trivial solutions for D for non-square D. Okay, let me write it like this. When D is not a perfect square. In fact, you can also assume D to be completely square free. For example, if you have 8. So if you have 8y square, so 8 is not a perfect square, but you can reduce the equation. You can just take 4 out. So this is same as some 2y square to say y dash square, where y dash is 2y. So if you can solve this, you can solve the previous one. So therefore, it's enough to assume that D is square. Yeah, we can in fact it is enough to solve for square free Ds. Square free. So if we know how to solve it for every square free D, then we have all the solutions. So I will send you a reference which gives you a general. So several general method of solving these equations, and one of the method is of course via this continued fraction. So very similar argument. So we just did a particular case that makes it a bit easier. Otherwise, it have some little bit of a complication, but it is. But this method works. Essentially, the same technique works, and convergence give you solutions. Yeah. So
But
sorry. Yeah.
In the general Bell's equation, actually, the right hand side is any natural number, need not be 1, right?
Yes, of course. Yes. Yes. Yeah. So yeah, very nice that you brought it up. Yes. So there can be not necessarily 1. It can be -1 or even any integer. So those are even more general things. So with -1, it's generally called this negative Pell equation. So I would send you a reference which covers all this. So it's a book on quadratic equations. So it goes into all the details. Yeah, so one short remark is about this name Pell's equation. So this is named after somebody called Pell, but it's actually very strange. So that name was given in a very strange situation, probably by people who are ignorant about other things. So this is very interestingly, this equation was known to ancient people from Greece to India. And we just mentioned, in fact, Budayana an Indian mathematician from 4th century, 4th century. So solved this equation, the equation we actually solved now. So that equation, and figured out this solution that xy is 577. Probably you knew other solutions, but that's what you might have used in some other work. And there was some very strange, very interesting history in that. Brahmagupta, that is 7th century. So he solved this with d equal to 92. So I'm not writing down the solutions just not to spend too much time on this. And then there was this solution by Bhaskara. So Bhaskara 2 actually. So these people also Bhaskara 2. So that's from 12th century. So that was x square minus 61y square equal to 1. So they all looked at this positive Pell equation. So since we actually talked about this minus 1, so they all looked at positive Pell equation because of practical applications. So they have some applications in mind in architecture and some other things. So he had a solution which I would just like to write down just to show how enormous numbers they could calculate. Just absolutely stunning. So this kind of solution, and he also proved that this is the smallest solution. Amazing. 319049. So enormous solutions. And then the next person I would mention is Pharma. Very famous for this Pharma's last theorem. So that is 1677. Sorry, 1657. 1657. He wrote down some Pell's equation in a systematic way, followed by Euler, who made it even more systematic. 1770. And so then the name somehow was attached to Pell because of some strange reason. Now it is also called this Pharma-Budayana equation or Pharma-Euler-Pell equation. So all lots of names are given to do justice to this history. So anyway, so it's a fairly interesting thing to do. Let me come back to some theory. Let me see what will do. So okay, so we know that this the convergence of continued fraction gives us good approximation to irrational number. They in fact provide best approximations in certain sense. So let's talk about that. Yeah, so we are back to theory. So approximations by convergence. Approximation by convergence. So what we intend to see is the following. I'm just writing it within quote because we will define it just immediately. So convergence provide the best approximation. Two irrational numbers. And let me explain what I mean. So let's write down two statements. Say A. So if n is greater than 1, wait for n greater than 1, and 0 less than q less than qn less than equal to qn less than. So it is a non-zero integer between q is a non-zero integer between 0 and qn. So qn is a convergent. Q and pn are our fixed notation. So they are convergent to a continued fraction x. And p by q is not equal to, so p and q are p is some integer, p by q is not equal to pn by qn, because we also have an option to take q to be qn, so, but we choose some different p, not pn. Then x minus pn by qn, the difference, x is the number we are trying to approximate, and pn by qn is the nth convergence. So this is less than x minus p by q. So this is what I mean by best approximation. So if we bound our denominators by denominator of a continued fraction and choose the numerator arbitrarily. So we have these choices. We can choose q between 1 and qn and choose any p, and just write that quotient p by q, that's a rational number. Rational number with only the condition that it's not exactly equal to pn by qn. Of course, if it is equal, then these two things what I wrote in the next line will become equal. So if it is not equal, p by q is not equal to pn by qn, then the distance between x and pn by qn is strictly less than that of between x and p by q. So pn by qn is closer than p by q to x. We can in fact prove a slightly stronger statement. So this is what we will prove. So same thing. So if n is greater than 1 and 0 is greater than 1, 0 less than q less than equal to qn, pn by qn is not equal to p by q, then qn x minus pn is less than qx minus p. So this linear form, so we consider this as linear form. So the first linear form is in absolute value is going to be smaller than the second with these values. Okay. So the convergence actually minimizes that linear form. Yeah. So I just said that B is stronger than A. Therefore, we should prove that B implies A. So B implies A. So let's see that. So suppose B is true. So Qn x minus Pn is less than Qx minus P. Then let's divide this by divide both sides by Qn. So you have x by Pn by Qn. That's less than x minus, sorry, this is Qx by P by Qn. So we just divided both sides by Qn. And Qn, Q is smaller than Qn. Therefore, if I replace Qn by Q, I get something larger. So Qx by P, absolute value, by Q. So we replace Qn by Q and get something larger. And that is exactly Q by P minus Q. So proving the claim. So it's enough to prove this statement B. So enough to prove the statement B. So Qn is between 1. It's not 0. It's an integer natural number starting from 1 and less than equal to Qn. It can also be equal to Qn. So let's start with that situation. So proof of B. Proof of B. Let's write that case 1. So Q equal to Qn. Start with this case. Q equal to Qn. So if Q equal to Qn, Pn by Qn minus P by Qn. So Q is Qn. So P by, so let's write P by Q, but Q is Qn. Q is Qn. So this is Pn minus P by Qn. And this is greater than equal to 1 by, because P cannot be Pn, as Pn by, as we have assumed that the rationals are different. So Pn by Qn is not equal to P by Q. So if Qn is equal to, sorry, if Q is equal to Qn, then P cannot be Pn. So therefore, this is not 0, and a non-zero integer in absolute value is at least 1. So this is 1 over Qn. So at least 1 over Qn. Let's continue. Okay. So as P is not equal to Pn, that's the logic. Now let's look at the difference Pn by Qn minus x. This is less than equal to 1 over Qn plus 1. That we already know. So we have proved it already. Which is less than 1 by 2 Qn. Because Qn plus 1 is certainly bigger than 2. So that's strictly less than this. That's also we have proved, that Qn plus 1 is greater than greater than n plus 1. Yeah. Now let's look at this P by Qn. P by Qn minus x. So P by Qn is our P by Q because Q is Qn. So this is the number. We want to show that this gives a so we want to show that Pn by Qn gives a better approximation. So we start with that and trying to bound it below by Pn by Qn minus x. And so use triangle inequality to insert Pn by Qn. So this is P by Qn minus Pn by Qn. So it is triangle inequality on this side. So it looks like this. And then you have Pn by Qn minus x. So it's just triangle inequality. And this difference, this difference, this is greater than equal to 1 over Qn, and this part, the next one, is less than 1 over 2 Qn plus 1. Sorry, I wanted to write Qn. We're going to compare. So, so Qn, both are true actually if n is greater than 2. But yeah, n is greater than 1 itself, this is fine. I can replace Qn plus 1 by yeah. So if I combine the first two inequalities, then what we can say is that whatever we have within the absolute value is positive. Therefore, we don't need the absolute value on the whole thing. We remove that, and that gives us 1 over Qn minus 1 over Q2Qn. 1 over 2Qn. This is 1 over 2Qn. 1 over 2Qn. But 1 over 2Qn from the previous inequality, we know that it is bigger than Pn by Qn minus x. So therefore, Pn by Qn gives a better approximation than P by Qn. So this is the first case. This is the first case. Now it's should I? Okay, it's 8 o'clock. So should I just continue tomorrow? I can do that because yeah, maybe I will continue tomorrow. So we have just a little bit of theory left of what I intend to do. So I'll continue tomorrow with this proof, and then what I want to talk about is pi. So far what we have seen are quadratic irrationals, which are easy to expand in continued fraction. Now the question is, how do you expand irrationals which are difficult, which are not quadratic irrational or does not satisfy any polynomial, in fact, with integer coefficients. So such a number is pi. You would know that it's called transcendental number. So pi is an example of a transcendental number. So that can also be approximated by convergence. One can write down the continued fraction expansion. For example, E is also such a number. So I won't be able to, I was thinking of doing pi and E both, but both would be too much. I can give reference to E. So what we would talk about is pi. There is a lot to talk about pi. So we'll do that tomorrow. Yeah, thank you for attending. So I will stop with that.
Okay, sir. Thank you, sir.